So let me finish my explanation on concavity. When the second derivative is greater than 0 on an interval, then your graph is concave up. Well, if it's concave up, let's just draw a quick example of being concave up. Simple parabola. What is always at the bottom of a concave up parabola? It's a minimum. Okay, so when you're concave up, you have a minimum at that critical value C in question. Okay, so vice versa, when f double prime is less than 0, so when it is negative, just as a reminder, that means negative, this one's positive. When it's negative on an interval, then your function is concave down on that interval. So negative down, positive up, we're kind of used to that with the first derivative. If it's positive, then it's increasing. If it's negative, then it's decreasing. So those things all go together the way we expect them to. If it is less than 0, if the second derivative, let me be specific. If the second derivative is less than 0, if it is negative, and it is concave down, let's think about a concave down parabola. A concave down parabola has a maximum. Okay, so those parts are just a little counterintuitive. Okay, we think positive, up, increasing, max, but just in my experience, the easiest thing to do is just think about a parabola. Okay, if it's concave up, it's like a cup, it holds that water, then you got a minimum. If it's concave down, it looks like a frown, then it has that maximum up at the top. Okay, here's something we have to remember though. We find our critical numbers for the second derivative, our possible points of inflection, by setting the second derivative equal to 0. But if when we plug that critical number, by setting f prime equal to 0, and we test them in the second derivative, but if f double prime of that critical number also equals 0, then our second derivative test fails. And we just have to go back to our first derivative test where we check a value to the left and to the right to determine the minimums and maximums. So let's look at an example of determining our points of inflection and the concavity of our graph. So let's find f prime of this function, x to the fourth minus 4x cubed. Then that derivative is 4x cubed minus 12x squared. But we're trying to determine points of inflection, so we want our second derivative equal to 0. So we are going to find the second derivative. So that gives us 12x squared minus 24x for our second derivative. We set that equal to 0. It's a polynomial, so we're always going to have to factor. There's a GCF here of 12x. When we take out a 12x, we're left with x minus 2. So let's set our two factors equal to 0. 12x is equal to 0. X minus 2 is equal to 0. So in this case, x equals 0 is a point of inflection, and x equals positive 2 is a point of inflection. So those are our points of inflection. Then it says determine the concavity of the graph. So let's set up a number line like we've been doing with 0 and 2, and we want to check values. I'd check -1, 1, and 3. We are checking these in the second derivative because we're curious about the concavity of our function. The second derivative tells us concavity. So I think it's easiest to plug it into the factored form because you really don't have to crunch the numbers that much. It's just a matter of what signs do we have. So when we plug in -1, 12 times -1 is a negative, and -1 minus 2 is a negative. So that means we are positive to the left of 0. When we plug in +1, 12 times +1 is a positive. 1 minus 2 is still a negative. So we are negative between 0 and 2. Our second derivative is negative between 0 and 2. And then when we plug in 3, we get a positive times a positive. So we are positive to the right of 2. So we are, let's see here. Let me use red for concave down. Between 0 and 2. And I'll use green for concave up. And that is from negative infinity to 0 and from 2 to infinity. And I didn't formalize our points of inflection, but we found them up there. Let me just write it down. Points of inflection at x equals 0 and at 2. Let's look at this graph, just because I want us to keep getting used to the idea of what it looks like to change concavity. So let me go back to my original function. There we go. Y equals x to the 4th. Please, please, please be trying to get used to those new calculators as much as possible. Just play around with them like you would a new cell phone. Look at all the menus. Look at the options. Google how to do certain things. They have explanations of how to do everything on that calculator if you just Google it. Graph it. And here's our function. It's a little, obviously I can't see the whole thing, but if we look at it, we're concave up right here until we get to 0. Then it's concave down. And then let's see here, let me adjust my window a little bit, make my Y nope, not my maximum. I need to, not 210. Let me change it to 5 because I'm not as concerned about the top of it. I need to see more of the bottom here. Let's look at the graph again. Concave up, concave down, and I still didn't go far enough, but I think you can see the change in these segments that I was talking about earlier, how they switch from this direction to the other direction, and then it's concave up.